He's like, why did a math teacher have to buy me? Deck of cards. There's 4 suits. They are hearts. Sounds like Lucky Charms, I know. Diamonds. Spades. Clubs. There are 13 cards in each suit. We'll call ace low just for now. They go ace, 2, 3, 9, 10. So you have an ace of hearts, an ace of diamonds, so forth, a 2 of hearts, a 2 of diamonds, so forth, all the way up to, what's the next thing? Jack. Queen. King. So we'll play aces low right now, just so there's a 1. So that's true for all of these. Bam, 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 bam. So there's a jack of hearts. There's a queen of clubs. There's a whatever. So you see how cards are just like probability questions just waiting, you know. This is why poker, the better you know probabilities, the better a poker player you are. Not on any individual game, but in the long run. And by the way, while I'm thinking about it, real quick. My little brother, let me give you a story. My little brother asked me, do you teach probability in your stats class? I'm like, yeah. He's like, that's just all shit, Jeff. All right, James. What do you mean? He's like, everything's going to happen or it ain't. All right, 50-50. There, leave those kids alone, Jeff. I'm like, my God, don't ever become a doctor, James. Right? You go into surgery, what's my chances, doc? 50-50? You know, I was like, I don't want that thought to be the last thing I think before they put me under. You know, so there is a place. His idea is after the fact, something happened. So just look what happened. I'd rather know the probability that the hurricane's going to hit. I'd rather know, give me some way, not just 50-50 for everything. 50% chance it's going to snow tomorrow here in San Diego. No, it's not 50%. Holy shit, that's way higher. What does it mean then? So for example, if I roll a die, right? If I roll a die, what's probably get a 5? 1 out of 6. I love it. So it's not a Dungeons and Dragons die. It's 6-sided die, right? Just in case some of you guys are like, hit points, I got a 20. 1 out of 6. What the shit does that mean? What in the shit? So for any specific roll, it doesn't mean a damn thing. Probabilities only start to really make sense when you do something a lot. So a really good poker player is one that plays the probabilities. That doesn't mean they're going to definitely win. It means in the long run, they're going to win enough to make good money. You play the probabilities, right? What does this mean then? In the long run. So this means that if I roll the die 1,000 times, let's make it 6,000, just to make this easier. If I roll a die 6,000 times, number one, I got to evaluate my life. But I'm like, what's happening, Jeff? Something's wrong. But how many 5s would I expect to show up then if I rolled it 6,000 times? How many 5s would I expect to show up? 1,000. 1/6 of them. So 1/6 of the time, I would expect a 5 to show up. So on a single roll, that don't mean shit. That's another reason why probabilities are not intuitive. They only tell me if this thing was to happen a lot, you should do this. Right? But on any specific thing, anything could happen. But in the long run, you'll be ahead in certain situations. So this one, if I roll a die 6,000 rolls, 1/6 of them will be 5s. Become a 5. So, later in the course, we'll talk more about, we'll bring standard deviation back in. We'll start to talk about, well, what would be unusual then? What would be an unusual number of 5s? Well, obviously, if I rolled a die 6,000 times and got 5,800 5s, what do I think is probably true about that die?
Loaded.
Somehow it's loaded. Somehow a 5 was good, whatever game this is, right? Or maybe you just got, this is my 5 die, this is my 4 die. It depends on the situation. No. You guys kind of with me? But what if I got 985s? Is that okay?
Yeah.
What do you think?
Yeah.
That's pretty close. So this idea of close, which again, deals with standard deviations, remember? Standard deviations tells you how close or far away something is. Not a good enough answer for a test, by the way. Right? But a general idea. So later we'll actually be able to tell how far away from 1,000 would unusual start. How far away from 1,000 would it be evidence that the die has been tampered with? You like it? So that's later. Okay. Sorry about the whole side trip there, but oh well. So coming back to cards. Let me ask you this. What's probably the idea of king? Well, how many cards are there? First off.
42.
There's 13 in each. 52. Right? If you had an older sibling like I did, then you know the game 52 card pickup. Okay. Jeff, 50 card pickup. Pick them up or I'm going to put you. All right, we'll pick them up. My older sister. I love her. So what's probably I pick a king? If I just pick a random card out of a normal deck of cards, no jokers, no shit, just 52 cards. What's probably get a king?
4 over.
Yeah, 4 kings out of 52. Which reduces to what?
1 over.
1 out of 13. Do you see the physical meaning behind this is easy? 4 kings in a deck, which means there's on average 1 king for every 13 cards. Do you see that? So if a probability reduces, very often it has a physical meaning to it. Very interesting. Will it help you with any problems? No. Just an interesting side note. Now let me ask you this. Let's probably pick a king given it's a club. So what's going to be on the bottom now? 13, because I know it's a club, so I can throw all the other cards out. Out of those 13 clubs, how many are kings? 1. Why is it no longer 4? Because I just threw out the king of spades and the king of hearts and the king of diamonds. Are king and club independent events? Yes, because 1 happened and you don't give a shit. The ratio stayed the same. 1 to 13, right? Well, what's probably I pick a king given, let me see if you guys are cool with this, face card. How many cards have a face on it?
3.
Yeah, 3, 6, 9, 12. Jack, queen, king have faces. The jack, the queen, the king. And there's 4 of those, right? Jack of hearts, jack of diamonds, jack of spades, jack of clubs. So there's 12 total face cards. 12 total cards that are looking at you. Either 2 eyes or 1. 1-eyed jack. So what's going to be the bottom now? Well, there's 12 face cards. Out of those 12 face cards, how many are kings? 4. So are king and face card, are they independent? No, because 1 happening changed the probability of the other one. This one, club happened. Going back to the earlier question, that means that I know the card was a club. I know that that is the kind of thing that happened. The probably king doesn't give a shit. Still 1 out of 13. I like it. Okay, I like it. So let's look at, we keep talking about this given. Let me do 2 things. I'm going to give you the symbol for what given is. I keep writing given out because I didn't want the symbol to get in the way yet. And then we'll look at the formula for given. Unforgiven. So, that line means given. This here? That's the symbol for given. So what's the formula going to be? Well, help me out. Remind me. Where's the bottom keep coming from? Why 13? Because I was given clubs. Why the 12? Because that's what I was given. So the bottom seems based on the given thing. So here, what's been given to me? B. So the given goes on the bottom. Now, why is this a 1? Why isn't it 4?
Because that was the first
Because if I'm given that it's a club, what's the only way it can be a king? If it's the king of clubs. Let me give you a visual. You guys ever seen a picture like this?
Yeah.
They're called Venn diagrams.
Yeah,
I don't use them a lot, but they do have a couple of things that make it easier to see. So if I'm given that B happened, whatever the shit B is, B happened, what's the only way that A could also happen? Is it where? Where does it have to be? Could this have happened? No, it's got to be here. What the hell is this?
11.
A and B. So why did I put a 1 there? Because there's one card that is king and club. So the top of it given is going to be and you're going to look back at the other problems we did that were givens, and you can verify that that's what we did. Now again, did I need to know that formula before we did these problems? This is what's interesting. We created that formula from doing these problems. So if I give you a problem like this, I normally don't give you cards because I know there's a lot of people that are not that familiar with cards, but they're so good. If I give you a problem where you just count shit, don't use the formula. Just count shit. Right? The formula very often kind of, you use it incorrectly because it's more complicated than it needs to be for a problem where I can see everything. So what kind of problem do I have to use a formula on if I just tell you, like, probability of A is 0.7, probability of B is 0.2, probability A and B is 0.57. Oh, holy shit, I got nothing to count. I just got stuff to plug into an equation. I got to use an equation then. Love you guys. All right. That's the formula for given. Here's a good skill that you need. Can you write the formula for probability of M given W? Doesn't have to be man and woman. We could be muskrats given watermelons. I don't know. What's the formula for that going to be? No, it's not men and women. Okay. M and who? M and W. Probably with W. Yeah. The given thing goes on the bottom. The two combined goes on the top. And again, you'll have this on your formula sheet for that quiz. We'll do a formula sheet for the quiz. Yes?
For it being independent, the probability of K equals 1/13, and the probability of K given the club is 1/13. So
So I'd say
because they equal each other.
independent. Did I go too far? Independent. Since probability of king equals probably king given club.
And then it's dependent. Probability of king given probability of
King and face card are two dependent events.
Yeah.
I like it.
So like on a test, what type of answer are you looking for?
For this kind of thing?
Yeah.
You ready?
Like, what would you have
This.
on the test?
This. Where you say 1/13 equals 1. So that would be a complete answer right there. So if I said our king and clubs are those independent events, you say yes, since this equals that, this number equals that number. So if you're talking about king and face card, are they independent? No, because probably king does not equal probably king given face card. And you put the numbers. That's it. It's a purely mathematical reason. You can't go, well, you could have a card that's face card and the king, so I don't think so. No. They are dependent because the probabilities change if I know one of them. Yes?
So is it safe to assume that if A and B overlap at only one place, then they're independent?
If they only have one element in their and?
Yeah.
All right. No, not necessarily. No. Definitely what's interesting, I don't want to spend too much time on this because this does get a little freaky, but Let me ask you this question. You ready? So there's a room full of cats and rocks. Okay? You with me? And let's say I'm somebody who has no sense of touch in my hands. I'll walk in. There's like the same number of cats as there are rocks. So going into the situation, what's the probability I would randomly pick up a rock? 50%. So I walk in the room blindfolded. Remember, my hands can't feel anything. Right? Answer Elias Johnson. I come in and I pick something up. What's the probability it's a rock? 50%. I take off my blindfold. It's a cat. Now what's the probability it's a rock? 0. So if you have mutually exclusive events, they are the most dependent things you could have. Because the minute it's one of them, the other one has no chance. So kind of like what you're on the edge of is the only way you could be independent is if you have an intersection, if you actually have a place where you overlap. Right? If you have, so I used to use cats and dogs, but a while back, you can see how old I am now, there's this show called Cat Dog. Yeah, you don't want to get into the biology of that too much, but how did it do this? So I was like, oh shit, so I can't use cats and dogs. So then I started using like ice cream and rocks or salamanders and something, it's just, there's no rock cat yet that I know of. Can't use rocks and lobsters because it's rock, lobster. So that's a little side note. If they are mutually exclusive, they have no chance to be independent. If they're mutually exclusive, what's true about this? So let's say this is man and woman. What's the probability I pick somebody who's a man and a woman? No. Saying they have to identify as one of them. 0 chance. So this given is always going to be 0. There's no way it could equal the probability of either one of them. So that's automatically dependent. Okay, that's a little side note. It might come up in 1 or 2 problems, but I normally try to not make it too big of a deal out of it because it's a little freaky. And you're like, everything today's been freaky, Jeff. Oh, shit.
So, and is dependent and or is independent, basically.
No. So you ready? 2 events can be independent or dependent. Period. 2 events can be independent or dependent. And is used in the test for independence. Sure, it's used in it. Sure. But it doesn't mean that and is one or the other. I use it to figure out if it is. All right. I love that. Now, what's the one thing we don't have a formula for? What formulas have we done? We've done an or formula. We've done a given formula. The one big thing that keeps coming up is there's no formula yet for and. Okay. This will be the last thing we do today, I think. Yeah. I want to let you out early since it's been nothing but me yapping at you. Just so you know, this Wednesday, most of the class will be you working on a little group thing. Right? So I won't talk as much. You're like, thank God for that shit. All right. Don't worry, you don't have to say it all that. I can read your brains. All right, so we got, let's remember what we got so far. We got the probability of A or B.
Yeah.
We got the probability of A given B. Just for shits and giggles, what's probably B given A? It could be, now if you're like, well, this B and A, Jeff, well, that's the same as A and B. Divided by what's on the bottom? No. Probably of A. I love it. So in general, in math, a formula gives you the form for something. So if I change the inputs, you just use the same form for it. That's what I call a form. So what the shit? How do I get the formula for and? Oh, okay. So let me. Some of you guys already realize this is a little algebra, and I got a formula for and, but I want it to make good sense. All right. So I have a very serious example, and I have a remarkably silly example as to why and is basically what it is. What do you want first? Silly or serious?
Start serious and then go
All right, serious
In the
first.
class.
So this is very serious. It made Jeff cry when he was a little boy. But the first time, I hate that I have to say that first time that the space shuttle exploded in '86. They used to take us, I lived in Florida, they used to take us out, we'd watch it go up, yay. That day, for some reason, we didn't go out. Somebody had a premonition, I guess. And when I heard it, I will never forget, I was in English class, and I heard that it exploded. I just started crying. I was a major space geek. You guys kind of with me? Yes, it exploded more recently, again, because it had, the heat tiles came off. Anyway, the reason it exploded in 1986 is because there were these things called O-rings in the fuel line. They basically were like valves. What do valves do? They make sure that things flow in one direction only, right? So if they don't work, things are going to flow the wrong way. And when you're talking about fuel, they're going to be a big problem, right? So normally the probability that these would fail, very tiny. On that day, it was icy. So they kind of got less, they were more rigid. They didn't work correctly. So the probability they would fail went up. Are you guys with me? So if I have, why would I have several O-rings in a row?
If one fails, then the next one will catch it.
Yes, it's sort of like if you live in a really bad neighborhood, how many locks do you have in your door? More than one. Because you're like, you get in my house, you better earn that shit. You better know how to unlock this kind of lock, and this kind of lock, and this kind of lock, and there's my dog, and then, yeah, you got a lot to get past, right? You guys kind of with me? Why do you do that? So that overall you have a higher probability of it succeeding, the whole thing. If you want to wake up really early for a final exam, you might set 2 alarms, right? I love the whole, my alarm didn't go, it went off the whole semester, and just today it didn't go off? I don't know about that. All right, so let's say that the icy conditions made these each have like a 0.2 probability of failing, so 20%. Now, it doesn't make sense to add them together because I have 3 of them. One of them would have a 20% chance of failing. I put 3 in so that I had a better chance of succeeding. I can't just add these and say, now it's a 60% chance of failing. Why did I put 2 more in there then? Holy shit. So I can't just add them. So what's the only way this could fail is if this one fails, and this one fails, and this one fails. If I add them, I get a higher probability of failing, which would go against our intuitive reasoning that that's why we put 3 in there in the first place, is to bring the probability down. So I want you to really think about this. 20% of the time, this one fails. 20% of those times, this one fails also. What the shit does of mean with percentages? What does of mean? I love you guys. You used to come out of high school and you just knew of meant multiplication. Bam. Of means multiply. How do you do 80% of 11.8? 0.8 times 11.8. What's 1/7 of 82? 82 divided by 7. Right? 1/7 times 82. Of means multiply. So 20% of the time this one fails. 20% of those times this one also fails. And then 20% of those times that last one fails. That's a lot of failing. Exactly. Because the only way, for example, you set like 5 alarm clocks. Because you're like, I gotta get this shit up. So you do your phone, you do your normal alarm clock, you have a call service, you have a roommate that's gonna come wake you up, and you have, I don't know, a rooster. I don't know, you have 5 things that are gonna get you up. The only way you're not gonna wake up in time is if they all fail, right? Power goes out, the rooster dies, your roommate didn't come home last night, whatever, right? So what's 0.2 times 0.2 times 0.2?
008.
Please, dear God, don't say 0.8. It's gonna, yeah.
008.
0, 0, 8. 1, 2, 3. 1, 2, 3. Yeah. Let me stop here. Now, obviously, on that day, these were even higher than 0.2. So far, what makes sense? In fact, this is a little counterintuitive. When you multiply 2 numbers together, does it get bigger or smaller? It's a trick question because it depends on the numbers. 2 times 3 is 6. It got bigger. What's 0.2 times 0.3? 0.06. So 2 numbers that are smaller than 1, they will get smaller when you multiply. We're investigating and. Is that the nice bouncer or the mean bouncer? And. I like my facial. It's the mean one. Right? Should decrease the probability of something happening. Why do I have multiple O-rings? To decrease the probability of failure. Why would you set multiple O-rings? To decrease the probability I get up too late. So that's and seems to mean multiply. Okay, here's my silly example. This is a serious example because I almost tear up when I'm talking about it. All right, here's a really silly example. Okay. I want to join a fraternity, right? I'm like Will Ferrell. And the hazing isn't anything terrible. I'm supposed to walk down this hallway, and every 3 steps somebody slaps me in this cheek. And every 5 steps somebody slaps me in that cheek. So how often will I get slapped on both at the same time?
1.
No.
Every 3 steps this cheek. Every 5 steps this cheek. So when's the first time? Yeah, 15.
15.
So what's the probability I get slapped on this cheek? 1 out of 3.
3.
This is 1 out of 5.
5.
What's 1/3 times 1/5?
Is 1.
15. So 1 out of 15 times I get slapped on both cheeks. Again, it's multiplication that gets me there. So and is basically multiply. I want it to make sense by itself before we do the algebra and just get the result. 1 step and I got the answer. I don't know if anybody noticed this. I've already got and in a formula. We got and in 2 formulas up here. So if I use this one, how do I solve for this?
Multiply.
Multiply by
PA.
P of A. So probability of A and B. If I multiply by probability of A on both sides, probability of A and B equals probability of A times probability of B given A. Or is basically add. But there's an adjustment if it's not mutually exclusive. And is basically multiply. But there's an adjustment if they're not independent. So let's do one example, one concrete example of this.
Dependent.
Sorry?
This is if they are dependent.
If, no.
No.
I mean, this is the general formula, period.
Okay.
If B and A are independent, what can you say? Oh, God, independent, there's. And there will be problems in the homework that say A and B are mutually exclusive, and people just read past that, and they try to do the problem, and they die. That is information, right? If I say that B and A are independent, what do you know is true? What's true about probability of B given A?
Equal.
Equals what? Probability of
Of B.
B. A happened, B didn't give a shit because I was told that they're independent. So if you read in a homework problem, if they say J and K are independent, write this immediately. It's information they're giving you. And then if that shows up somewhere, use it. So if A and B are independent, how can I rewrite this statement?
PA and B equals PA times PB.
That's the one time you can just multiply these two directly is if they are independent. And when can I just add these two and not care about this? When is this 0 if A and B are? When is this going to be 0 if they are
Independent.
mutually exclusive? I love you guys so much. If they're mutually exclusive, the probability of them happening at the same time is 0. I really want this analogy. So, or is basically add. It is straight up add in a certain situation. And is basically multiply. It is straight up multiply in a certain situation. So don't just multiply two things together for an and unless you know they are independent. So, one example of this, and then we'll head out. Oh, let's do this. Instead of cards, let's do poker chips in a bag, just to be so original. So say I have 4 red poker chips, 3 blue poker chips, and 2 green poker chips in a bag. We start off easy. If I pick 1, what's the probability I get a red one?
4/9.
4 over 9. I like it. Which is 44.4%. Now I'm going to say pick 2 with replacement. I've got to tell you, because how could I pick 2 poker chips? I could pick 1 and then feed it to my little brother or something, throw it away. That would be a different situation. With replacement means I pick it and then I drop it back in before I pick the other one. So there's 2 stages to this. Pick 2 with replacement. What's the probability to get a red and then a green? What was probably the first one's a red one? 4 out of 9. And then I drop it back in. Now what does that mean? All the probabilities go back to normal. They are independent then. So if I don't put it back in, they will become dependent. It will depend on what I picked first. So I drop that back in, now it's probably going to green. 2 out of 9. So 4 9s times 2 9s. Is 8 over 81, which is like 0.09 something. Whatever it is, nobody's going to help me out.
0.09876.
All right. Now, what would that look like if I did it without replacement? So probably red, nothing's happened yet. It's probably that first one's red. 4 out of 9, nothing's happened yet. And then I throw it away. Totally. What changes about the next one? How many greens are there in the bag? There's still 2. Now be careful. How many poker chips have I picked so far? 1. This doesn't mean I picked 4 poker. I'm picking 2. So I picked 1 red. This is the probability that it's red. Throw that poker chip away. There's still 2 green, but now there's only 8 poker chips. Let's do one more. Still without replacement. Probably get a red and then another red. It's probably the first one's red.
So 4, 9.
Then I throw that away.
And then
Now there's 1 less poker chip like before, but there's also 1 less red. 3 out of 8. I love it. Which is 0.333. I think 1/2. So it'd be 0.1666. Double check. You never know. Now we did an absolute shit ton of stuff today. That's a real measurement. Look at that. Wednesday I'm going to do just a little bit of lecture, and then we're going to spend most of the time just working on some stuff. I like it. Yes. Totally. I mean, that's what I was doing in my head here, right? 4, 1, or just throw it all in the calculator.